Today we're going to finish up final exam review. That's why I marked it part 2. And last time we met, we left off, we finished number 31 in the review document. Excuse me, number 30. We're ready to go with 31. So what we're looking at with 31 is a thermochemistry problem, and the answer is going to be, which metal is it? Of all those in the answer list, we're going to determine which metal it is based upon their specific heat. So we have to determine the specific heat. All right, so the problem says a 45.9 gram sample of metal. Sometimes it helps to, actually all the time it helps, when you have a problem like this, it's got a lot of information in it. You need to extract that information from the problem so you can see what it has, what you need, and because a lot of it might be just fluff, blue smoke. So the mass of the metal is 45, we'll do better than that, 45.9 grams. And the metal is heated to 95.2 degrees. So its initial temperature is 95.2 degrees C. And it's placed in a calorimeter with 120 grams of water. This is the mass of the metal. This is the mass of water. 120.0 grams. And the water's initial temperature is 21.6 degrees. So this is the initial temperature of the metal. This is the initial temperature of the water, 21.6 degrees. The final temperature, since you're putting this metal into that calorimeter with that water, the final temperature will be the same for both of them. Once they reach equilibrium, then the final temperature is equal to 24.5 degrees. All right. So remember that the calorimeter, remember there are 3 types of systems surroundings that we can have. Systems surroundings. Okay, if mass can go either direction and energy can go either direction, then you have an open system. If mass, it cannot go, then you have a closed system. But if your system is such that neither energy nor mass can move across that barrier between the system and the surroundings, then you have an isolated system. That's the kind of system we have in a calorimeter. So everything that happens in that calorimeter has to add to 0. All the heat transfers must be 0. All right. Having said that, what does that mean to our formula? Well, that means that 0 equals any heat change in the water plus any heat change in the metal. Has to be 0. Okay. All right. So what's the formula we use for heat change? Well, what we need is actually the formula for both of them is going to be Q equals the mass times the specific heat of the metal or water, depending on which one we're using, and then the change of temperature. And remember, change of temperature is final minus initial. Okay, so now we can set up our formula. So what's the Q of water? Well, the mass of the water is 120 grams. All right. What's the specific heat of water? We're given that in the problem. The variable in this problem is small c. Either one works. That's what S means. S means C in that problem, specific heat. So it's 4.18 joules per gram degree C. Okay, and what's the change in temperature of the water? Well, the final temperature of water is 24.5. And it started out at 21.6. Okay. So let me erase this so we don't get too confused here. All right. So that's the heat change for water. What's the heat change for the metal? Well, the metal is a different mass. It's 45.9 grams. And the specific heat for the metal, we don't know. That's what we want to know. What's the specific heat? So we can select from A, B, C, or D to choose the metal. Right? So this specific heat of the metal is our unknown. Temperature change. The final temperature is the same, 24.5, minus the initial temperature, 95.2. Okay. That's the thinking part for the experiment, for the problem. The rest of it is just number crunching. So you take the difference here, multiply that times that, that's one term. You take the difference here, multiply that, and that term is times specific heat of metal. And then you solve for your unknown. All right. So if we do that, and here on the board is shown how we do that. So one term is actually the first term in this problem is this part. The second term is this part. But when you add them all together, you get 0.43 joules per gram degree C. That's the specific heat of the metal. And if we look at our choices, let's see, where's my, here we go. If we look at our choices right here, 0.43 is closest to iron, right there. Let's see, can I do something here? Yeah, there it is, iron. 0.45, iron. So that's our answer B. All right. Let's see, let me check my email for messages. Okay. Let's get back to number 32. Oh, I forgot to write this up here. 31. That's 31. And let's see, maybe I can. $32. Nope, it's not going to let me. All right, we'll do it the hard way. All right. There we go. 32. Okay. We're still talking about thermochemistry. In this problem, But for this problem, what we want to do is find out what's the enthalpy for that reaction. Now we've learned two ways to discover enthalpy, to calculate enthalpy for a reaction that we don't know. Okay, we have a target reaction, and you can either use Hess's law if you have a combination of other reactions that can be combined to determine the enthalpy for your target. The other way is if you have heats of formation, enthalpies of formation for each of the compounds in your equation, the balanced equation. And that's the way we're going to approach this one, because here we have the different heats of formation for each of the compounds in our target equation right here. Okay. So first of all, you need a balanced equation. Well, let's read the problem. Why don't we do that first? Nitric acid, HNO3, was first prepared 1,200 years ago by heating naturally occurring sodium nitrate here, with sulfuric acid. And it produced sodium bisulfate, or sodium hydrogen sulfate, plus the nitric acid, right? That's what you want right there. And it comes off as a gas, so you have to condense it. You have to cool it down so it'll condense. Okay, calculate the standard enthalpy for this reaction. That's what delta H with that little zero. That's what they want, the enthalpy, standard enthalpy for the reaction. And it also tells you in the problem that the equation is balanced. Now you can check it for yourself, but it is balanced. All right, so if we have this equation, let's see, sodium nitrate, I'm going to leave off the phases simply because we don't have a lot of room. H2SO4 yields sodium bisulfate plus HNO3. Okay, so we're given these values for the heats of formation. Each of these heats of formation is listed there below the equation. So what's our formula for the standard enthalpy of an equation? Well, you sum up all of the products, right? And you have to have the coefficients involved in each one. Fortunately, the coefficient is 1 for each one. This is products. Well, actually, I should write it this way. Delta H0 formation for products minus the delta, the enthalpy of formation for reactants. Okay. So all we have to do is say, all right, sodium nitrate is minus 467.8. And that's kilojoules per mole. I'll just write it for the first one. And then we'll add, what's the next one? Sulfuric acid, minus 814.0, minus 814.0. And then we subtract whatever is inside the equation on this side. So we need sodium bisulfate, minus 1125.5. And then we add to that the last one, which was nitric acid, minus 135.1. There we go. Okay, so all we have to do is resolve that equation. And let me scroll because I think I have it embedded in the document. Here we go. So once we let's see if I got them right. Okay, what did I do wrong? Hold on. There we go. There we can see all of it once. Okay, products. NaHSO4. I did get it backwards. My apologies. These are the reactants. So what we're going to do is just change the sign like that. So we'll take these and subtract these. All right, so this is that group and this is that group. So if I don't make any more mistakes, the answer should be positive 21.2 kilojoules for that reaction, which is E. All right, that's 32. Let's see. Be sure there's not something hiding below. Okay, we're good. All right. For this one, we're looking at the structure of the atom and just figuring out what goes where. Right? We need to fill in the table, and we're starting with this particular ion of manganese. Right? So you remember the convention. That's the charge. This position would be for how many are there? All right, there's only one in this case. This is the capital A value, or the mass number, and the mass number is protons plus neutrons. We don't have protons listed. So what do? Right? It asks you for how many protons. Right? How do you get that? Well, you go to the periodic table and look up manganese. And we look at manganese and we find that it has 25 protons. Right? So 25 protons fills in the first slot. Then 55 minus 25 is 30 neutrons. Right? This is protons. This is the mass number. Right? So we got that 25, 35. Number of electrons. We have an ion. How do you make an ion? You don't change the protons. It is the balance between positives and negatives, but you can't change the protons or you'll change the element. Right? So you always get an ion from changing the number of electrons. So the number of electrons to be 3 plus, you're going to be 25 positives and you're short 3. So it should be 22 electrons. There you go. Atomic number is 25, mass number is 55, and the net charge is 3 plus. There you go. Knock that one out pretty quick. How about 34? All right, this is nomenclature. FeSO4. First thing you ask yourself, when you see a formula that has to be named, what type is it? Is it a type 1, 2, or 3? If it's a type 1 or 2, then the cation is the cation position is occupied by a metal. Yes, it's a metal. It's a 1 or a 2. Break the tie between 1 and 2. Is it an element, a metal, that can conceivably have more than one possible charge? Right? And most of those are transition metals. Not all of them, but most of them. In this case, iron does have the possibility of more than one charge, so it's a type 2. That means we have to specify the charge on iron when we write the name. So we would start off iron. This is the sulfate polyatomic ion, which has a 2- charge. That means with one iron, this one has to be a 2+. So we specify the charge on the iron as 2, Roman numeral 2, iron 2 sulfate. How about B? C2H3O2. We've got another polyatomic in this compound. Acetate. And we have a metal. Is it a type 1 or a type 2? Well, sodium is an alkali metal. And all alkali metals are a +1 charge. That's it. They can't have any more. So you only have to say sodium. Acetate. That's it. How about silver chloride? I just gave the name. Silver is a metal, so it's either a 1 or a 2. But silver is one of those transition metals that can only have one charge. It's always +1. So we only have to say silver chloride. And D, CaSO4. Calcium is an alkaline earth. Always a 2+ charge. It's a type 1 compound here. So this is calcium. And then we have a polyatomic ion, like we did up here. Sulfate. And the last one. N2O3. Type 1, type 2, type 3. They're both elements are nonmetals. That's a type 3. The type 3 convention says you just name the nitrogen and how many of them are there. Dinitrogen. Trioxide. That's it. For number 34. Let's see, do we only have 2, or does it bleed over into the next page? No, just the 2. Okay. Now we're going to go the other direction. We're going to write the compound from the name. Aluminum hydroxide. So how do you write that? Well, what's the charge on aluminum? Aluminum is in the same group with boron. And boron, aluminum, gallium, indium, they all have a 3+ charge. So if aluminum has a 3+, and hydroxide is a polyatomic ion with a -1, then you know you've got to have 3 of them. But the 3 has to go outside of parentheses. Polyatomics act as units. You cannot break them up. You can't change the subscript on them. So in this case, you have to have a 3 outside the parentheses to balance 3 minuses with a 3+. Sulfurous acid. All right. If we're going to name sulfurous acid, the naming convention for acids, first of all, acids always start with a proton. We don't know how many yet. And then you say, is there an oxygen in this molecule? It did not start with hydro. That means there is an oxygen somewhere. And it's based upon that, which is derived from a polyatomic ion. So remember, H's become ick, and ites become us. So this is not sulfate, but sulfite. And the sulfite is SO3 2 minus. So now we know that we need 2 hydrogens because each one is a positive charge. Right. So there's your compound. All right, 35. Oh, got scrolled. Let me see. Okay. Number 36 is the other way that we determine the enthalpy of a reaction through using Hess's law. Now remember, you need, first of all, you need a balanced target equation. Right? And I think we're given that right here. Yeah. This equation is balanced. And in order to get there and determine the enthalpy of this reaction, we have to add together any of these reactions that satisfy the addition to make this reaction. Remember, that's the first rule of Hess's law. All of the combining equations must add up to the target. That is, reactants have to be on the proper side, products have to be on the proper side. They have to have the right number, coefficients have to match in the end. And if there are any compounds or elements that are in these component equations that are not in the final equation, they must cancel during the addition process. So we have to remember the rules. If we have to flip an equation to get reactants and products on the proper side, you change the sign on the enthalpy for that reaction. If we have to multiply the reaction by some number, whole number, fraction, doesn't matter, that same multiplier is multiplied by or times the enthalpy for that reaction. So we're kind of short on time. So what I'm going to do is these are the target equations that gives us this one. But these have to be rearranged in such a way that they add together to give us the final target equation. And what I'm going to do is scroll down here. There we go. And what we see is we've got several equations that we're adding together here, right? We want this one in our target equation, and let's see, I'm missing. Oh no, this is the target equation. Excuse me. This is the target equation, right? So this one comes from the list, and calcium carbonate. Calcium carbonate is on this side, so we had to flip it. We had to flip the equation and change the sign right here. Okay, so we follow that procedure and we make sure that we've got each one covered. In this case, none of these are in that equation. So this one must have been used to cancel these items, one of these items here. So what I've done is underline the ones that are part of this equation. This one had to be multiplied by 2. No, it didn't, because we've got water here and water here, excuse me. All right, we've got 2 waters there. We've got a calcium carbide here, calcium hydroxide there, yes. Acetylene here. Yep, I think we had to flip that one also. And then this one had to be multiplied by 2. So if you do all those things correctly and add them together and cancel terms, then you should end up with the value here. minus 713 as your answer. I know I flew through that one, but we're going to run out of time. So I had to do it. And the evidence is there. All right, 37, right? That was 36 we were on. Yes, 37. Which of the following has the largest first ionization energy? Sodium or rubidium? All right. This is this refers to chapters on periodic trends. Periodic trends in the table are such that first ionization energy increases as you go from lower left to upper right. So first ionization energy increases in that direction. So that means if you go up in a group or you go to the right in a period, you're going to be increasing the ionization energy. Right? So where's sodium? Sodium's up here, rubidium's down here. So the first ionization energy should be highest for sodium. How about 38? Which of the following has the largest atomic radius? Okay. How about atomic radius? What's the trend there? The trend for atomic radius is that it decreases from left to right, decrease from left to right on a period, and it increases down through a group. So that means it decreases this way. That means the decrease is lower left, upper right. Now we're comparing nitrogen and oxygen. Right? So where are they located on the periodic table? Well, they're in the same period. Right? They're in the second period. Nitrogen is to the left, oxygen's to the right. So which one has the larger atomic radius? Nitrogen. Because if you go to the right, you're decreasing. So you go to the left, increasing. Nitrogen has the larger radius. $39. I have to scroll a little bit. Let's see. Get everything on there. There we go. We got 3 parts to this one. Part A. Indicate the hybridization of each nitrogen and carbon atom in the molecule. All right, so we've got carbon 1, carbon 2, and nitrogen for this molecule. H2, H, H, O, and we got an OH. Okay. So we need to, this is carbon 1, this is carbon 2, and there's your nitrogen. Okay, so remember, hybridization needs the same number of equivalent hybrid orbitals as you have groups in your VS-EPR format. So if we're looking for the number of groups, we find 1, 2, 3. 3 groups for this carbon, which means we need 3 equivalent orbitals. Start with S, and then you add 2 more. sp2. Okay, how about the second carbon? We got 1, 2, 3, 4. We got 4 groups. sp3. 2. How about nitrogen? Nitrogen could be a little trickier because nitrogen is like this and it has a lone pair. Right? Think of it as an analog to ammonia. Ammonia has 3 hydrogens and a lone pair. This one has 3 bonds and a lone pair. If you don't know that, then you're going to have to draw out the Lewis dot structure for the entire molecule. But having four groups there, a lone pair and 3 bonds, it's also sp3. All right. How many bonds are in the molecule? All right. Here's B. How many bonds? Well, you have 2 types of bonds, remember, the sigma bond and the pi bond. If there's a bond in there of any kind, it's a sigma. So we have 1, that's not a bond. It's not a bond. 1, 2, 3, 1. Oops, look at here. There's a hydrogen here. 1, 2, 3, 4, 5, 6, 7, 8, 9. You have 9 sigmas and you have 1 pi. So that's 10 bonds. Okay. And see, how many pi bonds are in the molecule? Well, we counted them up. There's 1 pi bond. That was 39. 40. Okay. These are a little more difficult. So I separated these, the next problems, into a bonus category. So if you're studying for the final, focus most of your energies on the first 39 problems. And if you know how to work those, then you should be fine for the final. But if you want extra credit and you need extra credit for your overall average, then you may want to spend a little time on these bonus problems too. All right. 40, you're holding 2 balloons. An orange balloon and a blue balloon. Orange and blue. The orange balloon is filled with neon. All right, let's just put this one in here. Orange with neon, and the blue with argon, right? Okay. The orange balloon has twice the volume of the blue balloon. So the volume of the neon, or the orange balloon has twice the volume. So the volume of the orange balloon is equal to twice the volume of the blue balloon. Okay. Which of the following best represents the mass ratio of neon argon? So what we want to know is mass of neon ratio to the mass of argon. All right, what do we know about these balloons? Avogadro said, as long as the temperatures are equal and the pressure is equal and the volumes are equal, you have the same number of particles. But if you increase the volume, like if all of these factors are the same, but the volume here is twice as big, that means you have twice the moles. So the number of moles of neon is equal to twice the number of moles of argon. We have twice as many moles. Okay. So neon is approximately 20. Is approximately 20 mass number, and argon is about 40, correct? Yeah. Is about 40 grams per mole. Well, if you have twice as many moles here, but they weigh half as much, then you should have exactly the same mass. Mass of neon equals the mass of argon. So this ratio is 1 to 1. Right there, A. All right, 41. Which of the following electron configurations is different from that expected? Okay. So we have calcium, boron, scandium, titanium, vanadium, and chromium. All right. So where do we see discrepancies? At least the ones that we've talked about. We see discrepancies in two places. In the middle of the transition period, as you move across. The middle and the end of the transitions. And we also see discrepancies in the middle of the P groups, right, between nitrogen and oxygen, or phosphorus and sulfur. Right, but we don't have any of those in here. So we're looking at transition elements. All right, so that means calcium is not a problem. How about scandium? Well, scandium is the first one of the transition metals in the fourth period. So it would have a 3D1, right? No problem there. How about titanium? Titanium has a 3D2, no problem there. Vanadium has a 3D3. There's no problem there either, right? Because we're looking at 1, 2, 3, 4, 5. This one has 1 there, this one has 2, this one has 3. Chromium has a 4s2 and a 3d4. Okay, here's what happens. That's what we would expect. We would predict from what we know about standard alphabets. But here we have 2 electrons there, and we have 5 suborbitals, like that, like that. What happens is the lower energy state actually puts one of these here over there, because half-filled d orbital is more stable than 2 in the s, where you have paired opposite spins and they're repelling one another. If you can separate that one out over here into its own orbital, it's much more stable. So this discrepancy is different than what you would expect for the electronic configuration from chromium. All right, 42. Choose the molecule with the strongest bond. All right. Strongest bond. So methane is going to look like this. All sigma bonds, all single bonds. Water is like this, with 2 lone pairs. Ammonia is like this, with a lone pair. And HF is like that. All right, which one has the strongest bond? Well, these are all sigma bonds. Sigmas, sigma, sigma, sigma. So we cannot, we need a tiebreaker. Like either they're all equal or one of them is stronger. So what we find is the strongest bond is due to the greatest difference in electronegativity. Right? Fluorine has an electronegativity on the Pauling scale of 4.0, and everybody else is less. So the strength of this bond is due primarily to the difference in electronegativities. Yeah, that answers the question. All right. 43. 3 samples of a solid substance composed of elements A and Z were prepared. The first contained 4.31 grams of A and 7.7 grams of Z. The second had, getting in the way. There we go. The second had 35.9% A and 64.1% Z. It was observed that 0.718 grams of A reacted with Z to form 2 grams of the third sample. So how does this demonstrate the law of definite proportions? Right? Remember definite proportions. Definite proportions simply means that when a compound forms from 2 elements, it doesn't matter what the source is, where it comes from. It will always have the same or definite composition. By mass, right? This was before, this law was proposed before the advent of moles, when we knew how many atoms were actually in the molecule. This is a mass relationship. So what's the ratio of mass for Z to A? Well, Z to A mass ratio is 7.70 to 4.13, 1.785. The second compound has Z and A in it, and its ratio is by percent. So the percent C, why would we use 64.1 divided by 35.9? Like that? Because percent is a dimensionless number. Well, you say that if I've got 100 grams of this sample, then 64.1 grams of it is Z, and 34.9 grams of it is A. So that ratio is valid, and it comes out to be 1.785 ratio. The ratio of Z to A for the third compound has to be calculated. It was observed that 0.718 grams of A, 0.718 grams of A reacted with Z to form 2 grams of ZA. Okay. So what is the composition of this one in terms of A ratio to Z? Well, Z is going to be the difference, right? 2 minus 0.718, which is equal to, let's see, 2, 8, 1. 1.82? Let's see if that's right. No, it's 2. 2, 1 point. It's 2. 1 from 9 is 8. 7 from 9 is 2. There we go. And then we have 1 left over. So if we ratio now C to A, we know what the ratio would be. Z is this value, 1.282, divided by A, which is 0.718. And that's equal to 1.785. Okay, so the ratio of each one of these compounds, they're actually exactly the same. These are, in fact, the first statement says 3 samples of a solid substance composed of A and Z. And the ratio is the same for each one. The mass ratio is the same. These 3 samples are of the same compound, and they always contain the same proportion by mass of each element. That's the law of definite proportions. All right, 44. All right, write the balanced combustion reaction with C2H5OH, which is ethanol, the drinking kind, as one of the reactants. So you have to know what a combustion reaction is. You take this compound, C2H5OH, and you have to add oxygen. Right? And what do you get? Anytime you take either a carbohydrate or a hydrocarbon, react it with oxygen, you get carbon dioxide and water. So we need to balance that equation. Now, you can use the budget method that I taught you. I just have carbon, hydrogen, oxygen. And on this side, you have 2 carbons, you have 6 hydrogens, and you have 3 oxygens. Right. On this side, you have 1 carbon, you have 2 hydrogens, and you have 3 oxygens. Let's see if I did that right. 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 9, 10, 11. So that's 9, 11. Okay. So where do we start? Well, we start with carbon, say 2 carbon dioxide, and that makes 4, 5 oxygens. Okay. And then we go to hydrogens, and we say we need 6 hydrogens. So if we put a 3 here, that gives us 6 hydrogens. But now we have 3 plus 4 is 7 oxygens. So we need 7 oxygens on this side. Well, notice the oxygens are in 2 different places. So that's really not a problem. Actually, it's a blessing. We need 7 oxygens. If we say 3 times that oxygen, that gives us 6 plus 1 is 7. There we go. So there's your balanced equation for the combustion of ethanol. Oop, I'm going to scroll down a little bit. And we're rapidly running out of time. So get rid of this thing. Oh, there we go. Okay. 45. Actually, we're almost to the end. Photogray lenses. Remember the photograys? They may not call them that now. Transition lenses. They, as you step outside in the summer in the sunlight, they respond to the sunlight by getting darker. Originally, they were called photograys. They incorporate small amounts of silver chloride in the glass of the lens. And the following reaction occurs in light, causing the lens to become dark. So that silver chloride then is responsive to the light. In fact, this is the same reaction that you get from old film, right? We don't use film much anymore, but used to be. The technology for film photographs was based upon this transition of silver chloride to silver and chlorine separate ions. Okay, the following reaction occurs when light hits it. So we get this reaction. And what we need is energy. and we get silver and chloride. The enthalpy chain for this reaction is 3. The delta H for this reaction is, let's see, 3.10 times 10 to the second kilojoules per mole. Per mole of silver chloride. Assuming all the energy is supplied by light, what is the maximum wavelength of light that can cause this reaction? Right? When we say maximum wavelength, any wavelength over that doesn't have enough energy, right? Because as wavelength increases, frequency decreases. And if you decrease frequency, you don't have enough energy, right? We go back to Planck's equation. H nu. Right? So we want wavelength though. So we have to use the substitute for this one, which would be H times let's see, speed of light, wavelength, frequency. So we want that one, it's C divided by wavelength. Okay. So how much energy is involved? Well, let's see. Let me scroll this a little bit. See how much I can get on there. There we go. So here we have the energy per mole and how many molecules that is. Says that for each molecule, right, the transition is based upon 1 molecule of silver chloride. Actually, it should be 1 formula unit of silver chloride. So we want to know how much energy that is. And if we do that calculation, we find that this converts to 5.148 times 10 to the minus 19 joules per molecule. Okay. Now we use this equation where energy equals that. Okay. We need to know the value for Planck's constant, which will be in useful information at the back of the exam. Right. So you can find it easily. And we want to include Planck's constant. We will include the speed of light, 2.99. I rounded it off there, 2.9979. And then the energy that's required here, right? And that gives us, let's see, the wavelength of light in meters, but we want nanometers. So if we do that calculation, we get 3.858 times 10 to the minus 7 meters. And then we want to convert that to nanometers. So you need to know the conversion factor for meters to nanometers, right? This is 10 to the 9th nanometers, right? 1 billion nanometers per meter, right? So then you get 386 nanometers. That's the minimum, that's the maximum wavelength that will cause this reaction to occur, right? So if you walk out, if we had a red giant as our sun, this wouldn't work because the wavelengths would be in the red range, which is closer to 600 or 700 nanometers. You need something 386 or less. So the ultraviolet light that's in sunlight is actually largely responsible for this reaction because it's much less than 386. It's closer to 200 to 250 nanometers. Much higher energy. All right, I think I have one more on this review. Okay, this one should be fairly fresh because we had this type of problem in our last exam, the last chapter exam. So we have these three molecules, A, B, and C. And A has a hybridization of sp3. That's given to you right here. Molecule B has two more effective pairs. So these are 4 pairs. 2 more pairs means 6. So you need, and you've used up all your S's, used up 3 of your P's, all the P's. You have to go to D's. So D2, sp3 will give you all the pairs you need for B. Molecule C consists of 1 sigma bond and 2 pi bonds. I think that's what that says. Just a second. Yeah, 2 pi bonds. 1 sigma and 2 pi's. Okay. So how do you get that? Well, remember, if you have 1 sigma, that's it. You can only have 2 elements, 2 atoms to give you 1 sigma. So the only way that you can get 2 pi's is to have a triple bond, a pi here and a pi here. Right? So that means you have a linear molecule, and the hybridization on either one of these has to be sp. Right? So this one's linear. 6 effective pairs or groups means octahedron, right here, and 4 means tetrahedron. And then you know the angles, right? The tetrahedron just had to memorize that one, 109.5 degrees. Whereas the octahedron, right, is formed like this, right, with your central atom, and you have something up here and something down here and here and here and here and here. So the bonds are formed like that. You can have a square, you can have a right angle here, 90 degrees. You can have a 90 degrees here. Or if you've got an atom up here and an atom down here, then you can have 180 degrees. So those are the possibilities, 90 and 180 for octahedron. And then linear is always 180 degrees, no other choice. Okay, I think that's it. And let me just make sure. Oh, no, we got one more. Balance the following equation. Okay, this one's going to take some effort. And it'll probably use up all the time we have left. Let me see. Just checking. I don't want to check too long. Now we got 2 more. All right, so we'll at least get one of them in. All right. So we want to balance this equation. This is where we start. Ki HN, oops, can't do that yet. NO3, HNO3 yields KNO3 plus NO plus I2 plus 4H2O. Okay. The problem with this one is that if you just go straight and try to muscle your way through with the budget method, you're behind the game. In other words, it's going to eat you alive. What you have to recognize is that we have a redox reaction here. And the best way to approach it is to balance the electrons first. Once you get the electrons balanced and coefficients, the initial coefficients established, then you can work from there through the budget method. So this is what the first step is doing. It's saying, all right, iodide is oxidized to iodine. Let's see if we get this out of here. There we go. And the transition there is a loss of 1 electron per iodine, but you have 2 iodines. So you have 6 electrons, 2 electrons for the iodines. Okay, that's where you start. So you go from here to here, and it's a loss of 1 electron per iodine times 2 equals 2 electrons. For the way it is right now. So if you have an oxidation, you know you have to have a reduction. So what's being reduced? Well, you have to calculate the oxidation states for each one of these. This one is +5. This one's +5. This one is +2. Okay. So what's happening is you're going from this nitrogen at +5 to this nitrogen at +2, which is a gain of 3 electrons per nitrogen. Okay. Now, at this point, it's not important that we have nitrogen in 2 different places. All we want to do is balance the electrons. So how do you balance 2 electrons against 3? You cross multiply. So if we multiply this one times 2, we get 6 electrons, and we multiply this one times 3, we get 6 electrons. So how do you get times 2 here? Well, you put a 2 there and a 2 here. Okay, that gives you 6 electrons on this arm of the redox reaction. On this one, we need 3. So we're going to say 3 here and 3 here. Okay, now that's where you start to do your budget method. All right. So I'm kind of short on space here, but let me see if we can do this. So we got potassium. We've got a nitrate on this side, but it breaks apart into 2 different ones. So we have to take every element separate. Hydrogen, nitrogen, and oxygen. So we start out with how many potassiums? 3. Right? Start out with 3 potassiums on this side and 1 on that side. Iodines. You start with 3 iodines here and 6 iodines there. We start out with 2 hydrogens here and 8 hydrogens on that side. Nitrogens. We start out with 2 nitrogens here and 1, 2, 3 nitrogens on that side. And oxygens. We have 3 times 2 is 6. And we have 4 here, 4 oxygens, and 2, 6, and 3 is 9. Okay. Let's see, I count those right. Oh. I'm so sorry. That's not supposed to be there yet. So the hydrogens are going to change. Let me see, where else did I mess it up someplace else? No, that was the bad one. Okay. So we do have 2 hydrogens here. But how many hydrogens do we have here? We have 2 hydrogens there and 1, 2, 3, 6 oxygens. There we go. Okay. So where do we start? Well, we want to leave the iodines alone for now because that's by itself. Right? Any elements on either side of the equation that are by themselves, we leave them to last. How about potassiums? Right? What if we do, or I don't know, how about iodines? Yeah, let's do iodines. So we got 6 on that side, we need 6 on this side. We change this one to a 6. That'll give us 6 iodines and 6 potassiums. Okay. Now, let's leave the nitrogens alone right now too, because they're odd even. Maybe they'll work themselves out. So what do we have left? We have potassium. So what if we make this one 6? That gives us 6 potassium. Now it changes the nitrogens. 6, 7, 8. 8 nitrogens. And 18, 20, 21 oxygens. Okay. All right. 6, 6, 2, 8, 21. What if we fix the nitrogens on this side? So if we say we need 8 nitrogens over here. Right, so we need to change that to 8. That gives us also 8 hydrogens. Right? Yeah. 8 hydrogens, and 3 times 8 is 24 oxygens. Okay, so 6, 6 hydrogens. What if we need 8 hydrogens? Would be 4 here, so that would make 8 there. That changes the oxygens. So we have 4 plus 2 is 6 plus 18 is 24. 24, 8, 8, 6, and 6. So our coefficients are 6, 8, 6, 2, 3, and 4. Cannot be simplified any further because we got a 4 and a 3, right, a 2, right? So you can't make it any simpler. That's the balanced equation. And I'm over time. Let me see what the last one is, if it's worth spending time on the last one. For the sake of the recording. Oh, this is a stoichiometry problem. We better take time to do this one. We'll finish this one up and that'll be it. Stoichiometry. All right, we haven't done any stoichiometry problems in this for this exam. So something's going to write. '48. So one of the major commercial uses of sulfuric acid is in the production of phosphoric acid and calcium sulfate. The phosphoric acid is used for fertilizer. In fact, phosphate rock is mined from the ground, and then it's reacted with sulfuric acid to remove the calcium from it. And what happens is the phosphoric acid then, as it is dehydrated, in other words, separated from the mixture, and dehydrated, polymerizes, and you get these long phosphate chains. And you can get up to, well, actually, most phosphate fertilizers will be 46%. Calculated as P2O5. But you can get up as high as 52%. That's the highest you can get. But it's a really hard climb from here to here. Most fertilizers are going to be 46. If it's pure phosphate, and they call that triple superphosphate. You know, that doesn't solve the problem. The problem is this reaction. Right? So this balanced equation is given to you. Calcium phosphate. Right? 3 sulfuric acid yields calcium sulfate plus 2 phosphoric acid. Okay. So, what mass of concentrated sulfuric acid? So we're looking for the mass here. at 98%. 98%, 98% weight. So the concentration of the acid, and it's aqueous, 98%, must be used to react completely with 100 grams of calcium phosphate. Okay. So, since we've got the balanced equation, we can basically ignore that side of the equation. We're interested in this side. And the ratio is 3 formula units of sulfuric acid per 1 unit of calcium phosphate. So let's find out how many units of calcium phosphate there are. 100 grams, and we need the molar mass of calcium phosphate. Right? So we have to add up calcium phosphate. Let's see. Let me scroll a little bit. It'll save me time in calculating it. 310.18. 310.18 grams per mole for calcium phosphate. So that's 100 divided by 310.18 is 0.3224 moles of calcium phosphate. Okay. Now, we want to convert this to moles of sulfuric acid, right? So we need a multiplier here for calcium phosphate to cancel calcium phosphate and leave us with sulfuric acid. And the ratio is 3 of these for every one of those. Right? So 3 times that value is 0.9672 moles of sulfuric acid. Okay, so what's the mass of sulfuric acid? Of 100% sulfuric acid would be this, moles on the bottom, grams on the top, and that is 98.08. Right, so that means this is, I'll just multiply myself. 98.08. So this is 94.86 grams of sulfuric acid. That's 100%. We want the mass of the solution. So another conversion factor is needed. So for this, for every point, and let's just do it like this, percent. For every 98 grams of sulfuric acid, we have 100 grams of solution. That's 96.8 grams of solution, of sulfuric acid solution. Let's see. Yeah, 96.8 right there. Okay. Oh, there's another one. Well, shoot. I think I've got time to do the other one. Let me scroll it. Looks to me like, to be sure, yeah. That's the last one. All right. So what do we have here? For 49, you got a marker that's going dead on me. What we have here is calculation of the molecular formula for this compound, ethylbutanoate. And you're given okay. The combustion of 2.78 grams of this compound leads to the formation of 6.32 grams of carbon dioxide and 2.58 grams of water. And the actual molar mass is somewhere between 100 and 150. So what's the molecular formula? All right, let me scroll just a little bit more. There we go. So the key to this problem is finding out what is the actual mass of carbon, hydrogen, and oxygen, right? It says right here, carbon, hydrogen, and oxygen only in that molecule. What is the actual amount in that compound? Well, if we have 6.32 grams of carbon dioxide, 6.32 grams of CO2, remember it was combusted in pure oxygen. So we can't get the oxygen from these products. We have to deduce. What we do know is how much carbon is in here. Right? So what's the ratio? Well, we need a conversion factor that gets rid of carbon dioxide and leaves us with carbon. Right? One carbon is 12.01 grams. Two oxygens, well, carbon dioxide is 12.01 plus 32 for the two oxygens. So that's why we have 44.01 grams of carbon dioxide. And that gives us 1.72 grams of carbon, right? So we know how much carbon was in the original sample of 2.78 grams. 2.78 grams of the compound. Right. How about hydrogen? Right. So we have 2.58 grams of water. This is actually how we would do it in the laboratory. These calculations are the same things you would see in the lab. So water is 18.02 grams, you know that, and hydrogen, two hydrogens is 2.02 grams. Okay, so that gives us 0.29 grams of hydrogen. So how much oxygen is there? Well, that's the whole compound. And this is how much carbon it is. And this is how much hydrogen it is. So what's left over? 0.77 grams of oxygen. There you go. Now you have the mass ratio of these elements in the compound. And we know how to determine the empirical formula from that. Okay. So we need carbon, hydrogen, oxygen, and we have carbon is 1.72 grams, hydrogen is 0.29 grams, and oxygen is 0.77 grams. So we just need to convert each one of these to moles so we can get the mole ratio. Right? Henry Ford, assembly line. All right, so oxygen is going to be 16 grams per mole. Hydrogen is 1.01 grams per mole. Carbon is 12.01 grams per mole. All right, so we get 0.143 moles for that mass, get 0.287 moles for that mass, and 0.048 moles for that mass. Okay. So if we make this one 1, because it's the smallest, 0.048, 0.048 and 0.048, then this one has to be 1. And this one goes into 0.287 about 6 times. And this one goes into 0.143 about 3 times. So that's our empirical ratio, C3H6O1. So what's the empirical weight for this molecule? It's 58.09 is grams per mole. But that's for the multiplier of 1. The actual molar mass is between 100 and 150. So if we multiply this times 1, that will get it. If we multiply it by 2, then we get 116.18. Right? That's between 100 and 150. If we multiply it by 3, then we've exceeded 150. So this is our multiplier, and our formula is C6H12O2. All right, that's the last one. We're done with our review. I'm pretty sure. Yep. And all this information here will be available in the final exam document. All you have to do is go back and look at previous exams. In fact, the very last exam we took has all of this in it. Because what I would do is for each exam, I just add information and it would accumulate over the, so the very last exam we had will have everything here in it if you want to see what's available. Okay, that's it. We're done and good luck.